In this video, we will focus on single-term algebraic fractions and their simplification. This will be done in lesson number 1. In lesson 2, we'll be working with combinations of algebraic fractions, that is, adding, subtracting, multiplying and dividing algebraic fractions. And finally, in lesson 3, we'll be considering simplifying the compound algebraic fractions. In lesson 1 of this video, we'll be considering single-term algebraic fractions and their simplification, that is, specific ways that one possibly could simplify such algebraic fractions. The outcomes for this first lesson will be revision of the basic knowledge on algebraic fractions, and secondly, the simplification of single-term algebraic fractions. To start with, let's have a look at some algebra basics, in particular the use of brackets. The following information about the use of brackets is most helpful when one works with algebraic expressions in general. Let us consider this particular expression, x plus y. This is whether x or y represents a real variable or a real number. We may swap the order. That is because we have the commutative law for addition that applies. Secondly, if we have the expression minus x minus y, in other words, both terms of this particular binomial have a negative in front, we may take this as a common factor, minus 1. We saw this in the first video on basic algebra, and we have left in brackets the expression x plus y. So we may take the negative as a common factor. Thirdly, if we consider x minus y as an expression, we may change this expression to y minus x by taking a negative as a common factor. In other words, to swap the order, when we have a negative between terms, we need to remember to take the minus 1 as a common factor. Number 4, exactly the same. It's just the order of x and y are now different. In number 5, this is an important property that we need to remember. If we have an expression x minus y to the power n, where n is some natural number, positive or negative, in other words an integer, or 0, then whenever this number is even, in other words a square or to the power 4, we can swap the order of the terms inside the bracket without changing anything else. In other words, whether we have x minus y to the power an even number or y minus x to the power an even number, it will be exactly the same expression. This is sometimes useful to remember. And in particular also, if this exponent n is uneven, like 1 or to the power 3 cubed, for example, then we may swap the order inside of the terms inside, but we must remember to compensate for the negative which will result to put a negative 1 outside the bracket. Now this is some basics about the use of brackets that may be useful to remember. Next, we consider the structure of a number fraction, or a rational number as it is known. A number fraction is a fraction which has the form a divided by b, where a and b are integers, and of course b can never be 0. The top part above the line is referred to as the numerator, and the bottom part below the line is referred to as the denominator of this number fraction. Remember, a and b are integers, any integer, positive or negative, but b is never 0, so the denominator may not be 0. Remember, division by 0 is not allowed in the algebra of real number systems. Examples of number fractions. Let's have a look at a few examples, well known, like a half, minus 3 over 4, 11 over 3, 17 over 213, and many more, infinitely many more. Also remember that negative for a number fraction can either be above the line in the numerator position, or I can decide to put the minus below the line with a 4. It will be exactly the same number fraction, or normally it's just put in front of the number fraction to indicate that it's a negative number fraction. Any integer that we know of is a number fraction. Did you notice that? Well, clearly the integer 3 can be written in number fraction format as 3 divided by 1. So can any other integer, minus 10 for example. And as I've mentioned, the negative may be above or below the line. It doesn't matter. It represents exactly the same number. Even the number 1 as an integer can be written as a number fraction. Now, all the number fractions form the set of so-called rational numbers. Those numbers that can be written in fractional form, as we have indicated. And the symbol for the rational numbers is Blackboard Bold Q. It's capital Q, but a special font called Blackboard Bold. We will now focus on the central concept of this video, namely an algebraic fraction, denoted by AF. An algebraic fraction also has the format a divided by b as indicated, where a is called the numerator and b the denominator of such an algebraic fraction. In this case, however, the a and the b are expressions representing real numbers, also referred to as variables or unknowns. And recall that the denominator may never be 0, so b in this case never represents the number 0. Let's have a look at some examples. Here are typical examples of algebraic fractions with only one term. In other words, single term algebraic fractions, where some of the letters of the alphabet are utilized in this case to represent unknowns or variables. Now, to simplify such fractions, one need to consider a concept called the greatest common divisor. In such a case, let's have an example. We have, for example, 20x to the power 2yt to the power 3 divided by 35x y squared s. So you can see that some of the variables above and below the line are the same as factors of such an algebraic fraction. Also, the numbers or the numerical coefficients of the numerator and the denominators are not prime numbers necessarily. So the first step would be to write the numerical coefficients of an algebraic fraction in exponent or index form. In other words, prime factorized above and below, as we did here, writing 20 as 2 to the power 2 times 5 and 35 as 7 times 5. And this will give us an indication of how to simplify by cancelling above and below to find the final simplified numerical coefficient of this particular algebraic fraction, 4 over 7. Similarly, we can apply our exponent rules for the quotient of exponent forms that you will find in the video on exponents and surds. You can have a look at those rules and its applications. We look at the exponent forms with the same basis, x for example. Above the line the exponent is 2, below the line its exponent is 1. Subtract 2 minus 1 and we're left with x to the power 1 in the simplified form. Similarly, we can actually simplify the exponent forms with the basis t, y and s respectively as indicated. So, simplifying by cancelling all common factors above and below is the process that will apply to simplify such single-term algebraic fractions. Let us briefly consider the restrictions linked to expressions with algebraic fractions. If the denominator of an algebraic fraction is 0, the expression is meaningless, as we've seen before. So, no factor in the denominator can thus be 0. Hence, the variable or variables in the denominator position cannot have certain values, as we will demonstrate with the following examples. Let us first of all consider the algebraic expression, which consists of two terms in this case, two algebraic fractions. In this case, it's clear that the restrictions for the variable x or the unknown x in this case will be that x cannot be equal to 3 and also x cannot be equal to minus 5. Did you notice what happens if x is equal to 3? 3 minus 3 is 0. Then we divide by 0, which is impossible. So we have to remove these values for the unknown x, namely 3 and minus 5, from all possible values that will be considered in this particular expression. It's not valid at all. Secondly, let's have a look at this algebraic fraction, which consists of one term. clearly above and below the numerator and the denominator positions, factorization is possible. If you consider the first video on basic algebra, we've discussed these processes. So above the line we can take the common factor x, unknown x in this case, and we're left with x minus 3. Below the line, this really represents, as you can see, the difference between two squares, which can be factorized in this way. Now immediately I see that there are certain values for x that are not allowed for this expression to be valid. In this case, the restrictions will be x cannot be equal to 2, and at the same time x can also not be equal to minus 2. These two values are not allowed as part of the x variable for this particular expression. We will now consider a general procedure for the simplification of single-term algebraic fractions. The first step would be to try and factorize both the denominator and the numerator of such an algebraic fraction. Secondly, one should attempt to divide both by the same factors, or cancel common factors above and below the line which defines the algebraic fraction. Note that only non-zero factors can be cancelled in this way. Let us consider an example to demonstrate this particular procedure. We start off with a single-term algebraic fraction as indicated, and we note that factorization is possible in the numerator as well as in the denominator position. So that will be the first step. Factorize both numerator and denominator where possible. In this case, above the line, in the numerator position, we may apply the difference of square type of factorization as discussed in the first video on basic algebra, and below the line we take out the common factor, minus 2, and write the denominator as indicated. Now we see that we have common factors above and below the line, which may cancel, but remember, we may only cancel these factors for values of the unknowns a and b, which will not result in a 0. We're not allowed to divide by 0. That is implicit in the simplification process of this particular type of problem. Next, we cancel the common factors. If that is the case, that the a and b does not assume values where a plus 5b is equal to 0, we may do that. And we have the simplification or the simplified form of our original algebraic expression. Note that the preferred format to write this is with a negative in front, not below in the denominator position or in the numerator position. The preferred format for the negative in such a case is to write it in front. So this is then a demonstration of how to simplify single-term algebraic fractions. In example 2 of the simplification of single-term algebraic fractions, we're given the following expression. Now in step number 1, we need to factorize both the numerator and denominator if possible. In this particular case, the numerator can be factorized using the common factor as well as the trinomial factorization methods. In the denominator position, we can take a common factor as well. So if we do that, we generate, in this case, a common factor above and below the line to be cancelled, namely x minus 3. Notice that we have taken minus 3x as a common factor in the denominator and not plus 3x, as to ensure that we have the order of the terms in the bracket correct, and this term should be then identical to the one above the line to be cancelled. So cancelling above and below, we apply, amongst others, also the exponent rule. Note also that we assume, in this case, that x is not equal to 3. Otherwise, this particular factor in the denominator position will result in division by 0. Note also that x squared divided by x, forces us to also apply the exponent rule for the quotient of exponent forms that we should be familiar with at this point in time. So finally, in the simplified form, the original expression reduces to, in this case, minus, in brackets, x plus 2 above multiplied by x in the numerator position divided by 3, as indicated on the screen. In example 3 of the simplification of single-term algebraic fractions, we see immediately, if we look at this given expression, that we have above the line 4 terms, which means we should try to attempt to use grouping to factorize for this part of the procedure. So, factorization stage 1 then would be identifying the pairs for the grouping factorization to be applied to the numerator position. In the denominator, we see immediately a common factor ax, and we take that to leave us with ax multiplied in brackets with x minus b. We can already see that we're aiming towards x minus b as a common factor above and below for this particular algebraic fraction, but we need to apply and complete the factorization using grouping before we can apply the cancellation as part of the procedure. So factorization stage 2 would then be to take the common factor from the first pair of terms above the line in the numerator position, take a out, and then we have x minus b, and we generate a common factor with brackets x minus b. We take that as a common factor with the final stage of the factorization for the numerator part, and now we have our common factor above and below the line, x minus b, which if we then cancel to complete, we have our simplified form of our original expression, namely a plus 1 divided by ax in this particular format. I think you're ready now to try the first tutorial of this video on the simplification of single-term algebraic fractions. I would like you to simplify the following algebraic fractions using the techniques that were discussed in this particular lesson. So 3 problems to do, and at this point in time I suggest that you pause the video, do tutorial 1, and then come back and view possible solutions. Let us have a look at the suggested solutions for tutorial 1. We had to simplify a number of algebraic fractions. This was the first one. This is a single term above and below the line of this particular algebraic fraction. We have a single term as well. So it's just a matter of simplification of the numerical coefficient for this particular algebraic fraction. And if we look at the prime factorization of 8 and 12 respectively above and below, we can reduce this through cancellation to the numerical coefficient being minus 4 over 3. Also, if we look at the exponent forms with the base a to the power 3 divided by a to the power 2, according to the quotient rule for exponents, gives us just a to the power 1 above the line. Similarly, the d to the power 4 above and below the line will cancel, and we have b divided by b squared gives us 1 over b, or b to the power 1 in the denominator position, while c just remains as part of the denominator in this case. So hopefully you managed to simplify your algebraic fraction in the same way. In the second case, second problem, we see that we have a common factor above the line in the numerator position, 2x. Take that from the numerator and be left with in brackets x squared minus 9, which is a difference between squares, which can be factorized using the standard decomposition for such an expression, namely x minus 3 and x plus 3. Below the line, of course, we also have a common factor x in this case, multiplied with x plus 3. So we see we have a common factor above and below finally, once we have applied the factorization steps of the simplification process. And finally, if we reduce, the x's will cancel, x plus 3 will cancel with the x plus 3. We have the expression 2 in brackets times x minus 3 to be the simplified version or the simplification of this particular algebraic fraction. In the third problem, we also have an algebraic fraction which can be factorized above and below the line, both in the numerator and the denominator position. If we look at the numerator in this case, we see that t is a common factor. If we take that out, clearly we have the difference between squares, namely t squared minus 4, which can factorize, as we saw before, using the factors t minus 2 and t plus 2 respectively. Below the line, we have a classical case of factorization of a trinomial. We have to be careful here to place the plus and the negative. There will be different signs for the two factors, since we have a negative for the final term, third term for the trinomial below the line. And in this case, we have the factorization as the factors t plus 3 multiplied with t minus 2. Just check that. 3t minus 2t gives us plus t for the middle term. Now we see that we have a common factor above and below the line, t minus 2, which cancels and will give us our final simplified version of this particular algebraic fraction in this case. In lesson 2, we consider the case where one works with combinations of algebraic fractions. In particular, we will consider the addition, subtraction, multiplication, and division of algebraic fractions. As we have mentioned, in this lesson, the focus will be on addition and subtraction of algebraic fractions, first of all, and then secondly on the multiplication and division of algebraic fractions. We will now consider a strategy for adding or subtracting algebraic fractions from each other. Let's have a look at this strategy. First of all, first step would be to factorize all the denominators where necessary. Secondly, you have to determine the lowest common multiple of each of these denominators of the given algebraic fractions. Thirdly, we have to write all the fractions as one fraction with the lowest common multiple as each denominator. Finally, we simplify the numerator of the resultant algebraic fraction if it is required. On the next slide, we will demonstrate how to apply this particular strategy in practice. Let us have a look at the different scenarios when we add or subtract algebraic fractions. In this case, we have the sum of two algebraic fractions with the same denominator b. Of course, b cannot be equal to 0. In such a case, the denominator of the resultant consolidated algebraic fraction stays exactly the same, and we only need to add or subtract the numerators as indicated on the screen. So this is the simplest case where we add or subtract two algebraic fractions together. Let's have a look at an example of this type of sum or difference of algebraic fractions. Here we are. Say we have the sum of the two algebraic fractions, both with the denominator 2x squared. All that we have to do is to add the numerators together, in this case to have our single algebraic fraction as the sum of the two that we started out with. The second scenario is somewhat more complicated than the first, in that we have two different denominators, b and d, both being non-zero in such a case, if we add or subtract two algebraic fractions together. We will demonstrate how to do this by using an example. Here we have the example, 2 divided by xy plus 4 divided by 3x, two different denominators, and in such a case we would like to find the lowest common multiple of these two denominators to start out with. In this case, this will be 3xy. Just check that you agree with this. We go about adding these two algebraic fractions together in the following way. We identify the LCM, as we have, and then we multiply the numerator of the first algebraic fraction with the LCM divided by the original denominator xy, as indicated. Add to that the product of the second numerator in the second term, multiply that with the LCM, 3xy, divided by the denominator of that particular second algebraic fraction, namely 3x. And we then divide everything by our LCM, because this will be the consolidated denominator of the single fraction that we will end up with. Can you see that in this particular factor in front of the original numerator 2, there will be cancellation. xy will cancel with the xy, and we only multiply the 2 with the 3 to find the new first term of the numerator in the consolidated algebraic fraction 6. And in the second case, you see that 3x will cancel with the 3x, and we only need to multiply the 4 with y to find the second term in the numerator position for the consolidated fraction. And of course, our consolidated new denominator will be 3xy, that is the LCM of the two denominators that we started out with. This is one way of tackling the problem. we could also do the following to add or subtract the two algebraic fractions together. We can just simply multiply across as we suggested before, okay, and then we can actually consolidate afterwards to simplify the algebraic fraction that we end up with. In other words, we can add these two algebraic fractions together by just multiplying the first numerator with the second denominator, 3x, add to that the second numerator and multiply it with the first denominator, xy, and then just simply multiply these denominators together to find the single expression as an algebraic fraction for the sum of the two that we started out with. This, however, is not in the simplest form, since in the numerator position we can see we have a common factor 2x. If we factorize above the line in such a case, we end up with 2x multiplied with 3 plus 2y, and then we can see that we have cancellation above and below. In such a case, the x will cancel, and we will have the denominator now equal to 3xy, as we had it before for the LCM in the first instance. And we can just multiply the 2 throughout, again if you wish to do that, to find the expression above the line in the numerator position to be 6 plus 4y. So it's exactly the same then as we had before. So there are two approaches then to adding or subtracting algebraic fractions of this type. We will now consider a number of basic examples of addition and subtraction of algebraic fractions. In the first example, we have to add these two algebraic fractions together. Note the denominators in this case are both numerical, 2 and 6 respectively. We still apply the same process. We look for the lowest common multiple of 2 and 6. In our case, it will be 6. So we have to write this particular difference of algebraic fractions as a single fraction with the LCM as the denominator. We have to compensate above the line, as we have demonstrated in the previous slide, by multiplying the numerator in the first algebraic fraction with the resultant, in other words with 3, because remember we have 2 already there, so 2 times 3 is 6, so we multiply it with 3 in the first case, and then we subtract, take the second numerator, that is for the second algebraic fraction, and we multiply that with 1, because the LCM in this case 6 will agree exactly with what we had before for the second denominator, or the denominator for the second algebraic fraction, so we multiply that with 1, and then of course times x plus 1. All that is left now is to simplify the new consolidated algebraic fraction, and to do that we look at the numerator position. We multiply out, in other words expand by multiplying 3 with x minus 2 and also the minus 1 with the x plus 1, and then consolidate like terms to be able to write this in its final form, simplified form, as 2x minus 7 divided by 6 in this case. In the second example, we have to add the 3 terms together as indicated. Note that in this case the number 1 is seen as a numerical fraction or a rational number, 1 divided by 1, and so x is also viewed as an algebraic fraction, x divided by 1. If we apply our strategy, and that is to write it as a single fraction with the LCM as denominator, so add these 3 algebraic fractions together, then we see that our denominator must be 2, because the LCM of 1 and 2 is just 2. And in this case we multiply both the first term and the second term by 2 as before. Use these brackets just to indicate 1 plus x together for the sum of the first 2 terms as we have it here. And then we subtract, in this case, the second algebraic fraction. We multiply by 1 and then the numerator 2x minus 1, since we have the consolidated denominator in this case is the same as what it was before. Now it's just a matter of collecting the terms in the numerator position, expanding and simplifying, and this is what we do. Multiplying the 2 out, we get 2 plus 2x, and of course multiplying the minus 1 with the 2x and the minus 1, we get minus 2x plus 1. Consolidate, 2x will cancel with minus 2x above the line, and we end up the final form of this particular sum of three algebraic fractions really as being just the algebraic fraction, which is in this case the rational number 3/2. In the third example of addition and subtraction of algebraic fractions, we look at a classical example of the sum of four algebraic fractions. We apply the techniques that were discussed before. So first of all, we attempt to factorize the denominators and then determine the lowest common multiple of each of these denominators. Recall that the number 1, in this case, the last term in this sum, can be viewed as 1 divided by 1, also an algebraic fraction for that matter. So the first step is to factorize the first denominator. We have the difference between two squares, and this should be familiar to you, the factorization. And also note that we have changed the plus for the third term, plus 1, as the numerical coefficient of the third term, to a minus 1. And that is to swap below the line for the denominator the b minus a to become a minus b, because we see we have as part of the denominator in the first algebraic fraction also a factor a minus b. That is to make sure that we have as few as possible different factors or terms to consider as part of our denominator set in order to find the lowest common multiple. So here we go. Write this particular sum now as a single fraction with the lowest common multiple of all the denominators as the new denominator of the consolidated algebraic fraction. Here we go. Clearly the LCM of the three denominators as well as the plus 1, which is the denominator of the fourth term, will be a plus b times a minus b, just the product of these two as we've seen. So in this case it's just a matter of multiplying the numerators in succession by the part of the new LCM denominator which wasn't previously present for the single term as such of this particular sum. So in the first term, a plus b times a minus b was the original denominator. It did not change, so the numerator stays exactly as it is. For the second term, the denominator a plus b must now be multiplied with a minus b above to compensate for the a minus b, which forms part of the consolidated new denominator for the single fraction. So therefore we have in this case a times a minus b in this case, and for the third particular term in this case, the minus b, the numerator, must be multiplied with what is now present as part of the consolidated denominator, which is the LCM of the denominators. So we multiply in this case by a plus b. You see, we had a minus b before, and this part must be multiplied above as well. And finally, the final term, plus 1, which we can view as 1 divided by 1, if the denominator becomes a plus b times a minus b, as it is, then above the line, the 1, the numerator in this case, must also be multiplied with a plus b times a minus b. Now it's just a question of expansion, consolidation of like terms to simplify this particular algebraic fraction into its final form. So the simplification step then involves the expansion, and we have had a look at the expansion of products of this type that we see as part of the numerator in this case in a previous DVD, so this should be familiar to you. We consolidate, and we see in this case that we end up with 2a squared minus 2b squared as the final form of the numerator. Of course, the 2 can also be taken as a common factor, and we can in fact in this case also again factorize and simplify. So did you notice that a squared minus b squared is exactly the same as the denominator a plus b times a minus b? So we have cancellation above and below, and finally in its simplest form the sum of the terms that we started out with just becomes the number 2. In the final part of this lesson we look at two more examples where we add or subtract algebraic fractions and where factorization play a role. Here we have the first example. Adding these two algebraic fractions together, we start by factorizing the denominators. You see that you agree with the factorization of the denominator of the first term of the sum. In this case, we take the common factor x, and we also have a trinomial factorization. And in the second term, the denominator in this case, if you take the common factor 2, becomes 2 times x minus 1. We also now note that factorization in the numerator is possible for the first term, and if we take minus 2 as a common factor, we generate two factors, x plus 2 above and below the line for the first algebraic fraction. So, after we have factorized, we need to simplify before we try to consolidate and add these two fractions together. And that we do by cancelling the x plus 2 factors above and below for the first term. Okay, now we try to find the LCM. That is the LCM of the denominators now, which consist of the set x times x minus 1 and also 2 times x minus 1. If you consider those two terms and look at the LCM, lowest common multiple, we see that becomes 2 times x minus 1 in this case. X minus 1 is common to both those denominators, so you need only repeat that once in the LCM as such. Also, if we now consolidate into one specific algebraic fraction using the LCM as the new denominator, then we can consider the top part, in this case, to be multiplied by just by 2. Yes, that is what is short here for x times x minus 1 to become 2 times x minus 1. We only multiply the numerator with plus 2, which becomes minus 4. And then in the second term, the numerator must be multiplied, in this case, just by x. That was the missing factor, which forms part of this particular LCM in this case. So finally, our consolidated single algebraic fraction, the sum of the two that we started out with, will be x minus 4 divided by 2x times x minus 1. That is then an example of how we utilize factorization to simplify first of all before we apply the LCM technique to find the sum of the two algebraic fractions. Okay, there we have the LCM in this case of 2 times x minus 1, and x times x minus 1 again just gives us what we have utilized in this particular instance. We have in the second example the sum of the two algebraic fractions as indicated, slightly different to what we had before, and clearly the same procedure applies. First factorize, see that you agree with the trinomial factorization below. Again, the common factor minus 2 above, common factor 2 for the second term, 2 times x plus 1 is what result there, and this is the difference of squares. X squared minus 1 is x minus 1 times x plus 1, and we have generated in this case factors, common factors above and below for both terms. First simplify that before we add or subtract, in this case, the two algebraic fractions from each other. So the LCM in this case will be x plus 5 times x minus 1. If we consider these two, it's just the product of the two. So we utilize this particular consolidated denominator for the single term algebraic fraction, and we compensate above by multiplying the minus 2 in the first term with x minus 1 that was missing, and in the second term the minus 2 must be multiplied with x plus 5, and then we expand in the numerator position and consolidate and check that you get minus 4x minus 8 in this case to finally give us this particular single algebraic fraction as the difference between the two that we started out with. Just check that you agree with the final numerator in this case. Clearly we can take minus 4 as a common factor and write this in factorized form, but it is not necessary in general to do it that way. We have considered quite a number of examples of addition and subtraction of algebraic fractions and the technique that should be utilized in that particular instance. So I think you're ready now to tackle tutorial 2, and here we have a number of expressions where you have to add or subtract algebraic fractions. Here we go. 3 problems in this case. And at this point in time, I suggest that you pause this video, do tutorial 2, and then come back and view possible solutions. Let us briefly consider the suggested solutions for tutorial 2. In the first problem, we had 3 terms to be consolidated into one algebraic fraction in this case. And after carefully considering the denominators, 3 denominators as indicated, we have the lowest common multiple, in this case a times b times c, which becomes the denominator of the consolidated algebraic fraction. Similarly, for the denominators in terms 1, 2 and 3, we had missing factors in the first instance a, the second instance c, and in the third instance b. If we consider and compare the denominators for each term individually with that which we have now for the consolidated fraction. Hence we have to multiply above the line respectively with a, c and b. That gives us the a squared plus c squared minus b squared as the numerator of this particular algebraic fraction that we end up with. In the second instance, we had to subtract these 2 algebraic fractions from each other. We start by looking at the LCM of the denominators, 4 times a plus 1 and 5a. So the LCM of 4 and 5 clearly is 20. And then we have to multiply with a and also with a plus 1 to form the denominator for the consolidated algebraic fraction, that is the difference of the 2 that we started out with. Above the line, for the first numerator, or the numerator of the first algebraic fraction, we need to multiply by 5a, in this case, because we already had 4 times a plus 1. So we only need to multiply with 5a to compensate for the fact that we now have 20a times a plus 1. And this, of course, is the same treatment for the second term. So minus 4 in this case is what we have to multiply together with a plus 1 again to form the new numerator minus 4 times a plus 1 all squared in this case. Remember, the denominator was 5a. We multiply with 4 times a plus 1 into a plus 1, and we have the new numerator as indicated. Now it's just a matter of expanding and consolidating like terms in the numerator position for the single algebraic fraction as indicated, and make sure that you agree that this is what we get for the numerator, a squared minus 13a minus 4. It's a little exercise for you to check that in fact is our final numerator for the difference of the 2 algebraic fractions in the end. In problem 3, we have 3 terms, 3 algebraic fractions that we have to consolidate into one algebraic fraction as before, and again it's just a matter of finding the lowest common multiple of the denominators, 4x, 6 times x minus 1 and 3. Looking at the numerical coefficients 4, 6 and 3 in the denominator positions, our LCM is 12, and then of course we have to also multiply with x and x minus 1 to find the LCM in this case for the 3 terms that we started out with, that is the denominators for the 3 terms. So above the line again, we have to consider each numerator separately. So 3x minus 5 in the first instance must be multiplied with 3 times x minus 1. Okay, so we had again a 4x there. Now all that we need is another 3 times that to have 12x, and then also the x minus 1, so we must actually get the 3 and the x minus 1 as part of the numerator in this case, to be multiplied with what we had before, 3x minus 5. Similarly, for the second numerator, we multiply the 7x minus 1 with 2x, and there's a negative in between because we're subtracting. And in the third instance, just check that the x minus 1 in this case, we need, in this case we had a 3, so we need 4x to be multiplied with x minus 1, in this case as the third numerator as part of the consolidated algebraic fraction. Again, just a matter of expansion. Check the first video on basic algebra if you're not certain how we expand such products, consolidate like terms, and finally we end up with a trinomial as part of the numerator for this consolidated algebraic fraction in this case, namely minus x squared minus 26x plus 15. Please check that you get this particular trinomial. Next, we consider the multiplication of algebraic fractions. Here is the format for such a multiplication of two algebraic fractions, as we can see on the screen. So if you had to multiply a over b with c over d, then clearly the numerators gets multiplied together and the denominators gets multiplied together. That's the basic format of the multiplication of algebraic fractions in general as well. So note also that if there's a sign in front of an algebraic fraction, we may position the sign either in front or in the numerator position or in the denominator position. It doesn't really matter, although the preferred positioning will be in front of such an algebraic fraction. You also have to recall, before we show some examples of how we apply the multiplication of algebraic fractions, that if you multiply same signs together, minus with a minus or a plus with a plus, we have a plus, and different signs multiplied together gives us a negative. That also forms part of the simplification in many instances if we multiply algebraic fractions together. So let's have a look at examples. First example, we have an algebraic fraction, as indicated, multiplied by a second algebraic fraction, which is negative. So the numerical coefficient is minus 2 for the second one, and for the first one is 24 over 8. So as we have indicated, we multiply the numerators together and the denominators together in such a case, and then we simplify. First of all, we can also consider the sign. The first one is a positive and the second factor of this product is a negative, so if we multiply, the final product will be a negative. After that, we can multiply the numbers together. That is, we can multiply 24 times 2 and divide by 8, and then simplify as well. In this case, simplification gives us plus 6 above the line. And then finally, we always have to try to utilize the exponent rules for exponent forms with the same basis, either the multiplication rule or the division rule. In this case, we see that if we multiply together, we have x to the power 3 times x gives us x to the power 4. The exponent rule applies, and we have a y there as well. And below the line, we have the same for the a times a becomes a squared. And in this case, the b squared gets retained. We also have x to the power 3 below the line. Now suddenly, we can apply the quotient rule for exponents and consolidate. And you can see that the a squared will cancel with the a squared, b squared will cancel with the b squared, and in this case, x to the power 4 divided by x to the power 3 gives us x, and the y gets retained to finally give us this particular expression, minus 6x, as the product of the two given algebraic fractions. More general, we may also multiply more than two factors together and apply exactly the same principle for the multiplication of algebraic fractions. We can have any number of such fractions multiplied together, and the same principle apply. We multiply all the numerators together and all the denominators together, and then afterwards we simplify exactly the way that we've illustrated with this example. So if we apply this particular strategy in this case, we see that we get the product above the line of the three numerators and the product below the line for the three denominators. If we consolidate first of all in the numerator position, use our exponent rules, and we should get in this case 2 times x times y to the power 3, a squared b to the power 3. If we consolidate the exponent forms with the same basis, using the exponent rules. Below the line as well, for multiplication, we multiply the numbers first, and then we consolidate the exponent forms with the same base to have y to the power 3, b squared, and a squared as part of the denominator as indicated. Note also that in this case we add a positive times a negative, a positive times a positive times a negative for the three factors, so we can consolidate the sign of the product immediately as being negative and write it in front of such a consolidated algebraic fraction in this instance. If we apply our exponent rules now, the quotient rule, we see immediately that we have some cancellation and reduction in normal way, and we finally have the product in this case to be minus 2 divided by 15 times x a squared times b. Just check that you agree with this. Let us consider another example of multiplication of algebraic fractions where factorization also plays a role. Let's have a look at this particular product of algebraic fractions. The first step in this case would be to factorize all the numerators and the denominators. So let's do that. In the numerator position for the left-hand side factor, we take the a as a common factor, and below the line, in the denominator position, we see we have a difference of squares, which will factorize as x plus 2 multiplied by x minus 2. That all multiplied by, on the right-hand side, we take the x as a common factor in the numerator position, and below, we have a classical trinomial factorization. Just check and see that you agree with this particular factorization of the denominator in this case. The next step would be to try and cancel common factors. That is, across the first and the second factor, or in the first particular factor algebraic fraction in this case as well. We see that we have common factors which will cancel in this way. The x minus 3 with the x minus 3 below the line, x minus 2 in the numerator on the right with the x minus 2 factor in the denominator on the left. And this then will finalize and simplify the result. Finally, we can write this as can be seen on the screen, namely ax above the line, that is the product of the numerators which remain, divided by the product of the denominators which remain after the cancellation in such a case. Next, we consider the division of algebraic fractions. Now this is what we typically have. A fraction, algebraic fraction, divided by another algebraic fraction. Now this really means that in this case the terms b, c and d can never be 0. Remember, division by 0 is not allowed, so d cannot be 0, b cannot be 0. And as you can see in this case, instead of dividing by the fraction c over d, we change this into multiplication by the so-called reciprocal of the fraction c over d, namely d over c. So in this case we also need c to not be 0 as well. So the reciprocal is the key element in the division of algebraic fractions, since we change such a quotient of fractions to become the product with the reciprocal of the denominator fraction. This is the denominator fraction. We change the order here, as you can see. In other words, we find its reciprocal, and then we change the division to a multiplication, and we handle this exactly as we did before. In other words, the numerators gets multiplied together, and the denominators, once we have changed the quotient of fractions to the product of two fractions in this way. Okay, so multiplication with the reciprocal is then what we have to do in such a case, changing the denominator fraction, use its reciprocal and multiply instead of divide. Recall also that for the quotient of any two signs, we have that same signs gives us a positive for a quotient, and opposite signs, if you have the quotient in this way, then we have a negative, as we would probably know at this stage. Let's have a look at an example. First, a numerical case where we have a numeric fraction or a rational number, one of them, minus 2/3, say, divided by another a rational number or algebraic fraction for that matter. Remember what we said? We change the denominator to its reciprocal in this case. There we go. These are reciprocals of each other. And we change the division into a multiplication. After that it becomes straightforward. We multiply numerators together and denominators together in the normal way, and we find the result in this case is 8/15 in such a case. Another example, let's say we have 4/7 divided by minus 3/8. Changing the division into a multiplication, we must find the reciprocal of the right-hand side factor of such right-hand side, or the denominator rather, of such a quotient. So minus 3 over 8 becomes 8 over minus 3, and then we multiply in a normal way the numerators multiply together and the denominators in this case, and there we go. We have a third factor here of the product to be considered, so we multiply all those numerators together and all three the denominators and get the result, in this case 64 over 105. Hopefully this gives you an idea how to handle the division of algebraic fractions. We will look at more examples on the next slide. The next example shows a case where we have a combination of multiplication and division of algebraic fractions. So let's have a look at this particular example. We have an algebraic fraction divided by a second algebraic fraction and then multiplied by a third algebraic fraction. Now what would this first step be in this case? Clearly, division should be changed to multiplication, as was demonstrated in the previous slide. So instead of dividing by this particular algebraic fraction, the second one, we have to multiply by its reciprocal. And after that we need to attempt to factorize all the numerators and denominators of such algebraic fractions, which makes up this particular expression. So let's do two steps in one. In other words, we have a look at the reciprocal of the second factor algebraic fraction in this case, and we factorize at the same time. So you can see x is a common factor below the line in this case, so this becomes x times x minus 8, but now in a numerator position, since we have considered the reciprocal of this fraction. X squared minus 8x plus 16, the numerator, can be factorized. We recognize this as a perfect square, in other words x minus 4 all squared, and this now becomes the new denominator, and we change the division to multiplication at the same time. If we factorize the first and the third algebraic fractions as part of this particular expression, then we have the following. X minus 4 times x minus 8 gives us the trinomial factorization for the numerator of the first algebraic fraction in this case. And if we move to the final part of this expression, we see above the line x is a common factor, so we have x times x minus 4. And now we're ready to cancel or to simplify before we write this particular consolidated the quotient and product of algebraic fractions as a single algebraic fraction. So we cancel the common factors. There we go. Just check. All those agree with what we have done before. Cancellation above and below the common factors as indicated. And finally, we write down the simplified result for this particular expression, which is a combination of the quotient and multiplication of algebraic fractions. Let us have a look at the second example of division of algebraic fractions. In this case, we have an expression a divided by 4b, an algebraic fraction, divided by the product of two algebraic fractions as a unit, indicated by this particular bracket that we have here, the square brackets. How do we handle this? Well, one can start by factorizing all the numerators and the denominators of these algebraic fractions, which makes up the expression, or one can change immediately this division to multiplication. The order doesn't matter. So in this case, let's start by factorizing all the numerators and the denominators. See that you agree with this. Your factorization skills will be very important in this particular case. So in the numerator position, 2a squared minus 2a, we take 2a as a common factor as indicated. The trinomial factorization gives us a plus 5 multiplied by a plus 1 in this case. And similarly, for the second factor of the product in the square brackets, this algebraic fraction, the numerator, we see that a plus 5 is a common factor. Yes, 5 plus a is the same as a plus 5. We take it as a common factor, and we're left with the factor 1 minus b in such an instance. Below the line, the denominator position as indicated, we have 4b as a common factor into a minus 1. Now the next step would be to change the division into multiplication. And this is done by considering the reciprocal of the expression in the square brackets. Now just note here, we have a product of two algebraic fractions, and if you consider the reciprocal of such a product, you know, the order of the numerators and denominators in both cases will then just be reversed. So the denominators becomes the numerators for the product, and in this case the numerators becomes the denominators as indicated for this particular product. And of course our division now changes to multiplication. So this is just a product then of three algebraic fractions in a normal way. And can you remember how to handle this? All you have to do is to multiply the numerators together as well as the denominators. But first of all, check and see if you have common factors above and below the line for these particular factors, and cancel across all three of these factors if necessary. That is what we do next. We notice that we have a number of common factors above and below. The a's, for example, a minus 1 is common, the b is common, 4 is common, a plus 5 is common, and once you cancel all of those, we can write this result in simplified form as follows. A plus 1 above the line is all that remains, below the line 2 times, and then the factor 1 minus b as part of the denominator of the resultant algebraic fraction. I think you should be ready now to tackle a tutorial on the multiplication and division of algebraic fractions. So in tutorial 3, I would like you to simplify the following expressions completely. Here we have 4 problems where we have products and quotients of algebraic fractions combined in most cases. At this point in time, I suggest that you pause this video, do tutorial 3, and then come back and view the solutions. Let us briefly consider the suggested solutions for tutorial 3. In the first part of this tutorial, we considered a product of two algebraic fractions and then divided by a third algebraic fraction. In this case, clearly, we have to factorize the numerators and denominators and then change the division into a multiplication. In this case, we start with the first algebraic fraction, recognizing the difference between two squares, and factorize as indicated on the screen. And then finally we change the division to multiplication, but notice that the b minus a in the denominator position now becomes minus in brackets a minus b in the numerator position. Why is that? Well, we notice that we have a factor a minus b, and if we take the negative as a common factor in this case, we will also create a common factor above the line a minus b at the same time. So always be on the lookout, to take out a negative in order to change the sign of the resultant terms in the brackets to then create a common factor which will simplify the expression in some cases. Now here we have multiplication instead of division then, and we have reciprocal. The b numerator now becomes the denominator in this particular factor of the product. Since this is only products of algebraic fractions, we multiply together above and below as normal after we have cancelled, and if we cancel the a minus b above and below as well as the a plus b above and below, and then also the a and the b will cancel, we end up with the result of this particular expression in simplified form as being minus 2. In the second tutorial problem, we again have an algebraic fraction divided by a second one multiplied by a third one as indicated on the screen. Now the process is exactly the same again. Find the factors or factorizations above and below for the numerators and denominators respectively. Change the division into a multiplication by considering the reciprocal of the middle algebraic fraction in this case. And if you do that, do you see that you agree? At the bottom of the first factor for this particular expression, the denominator here, we see this as a perfect square, a plus b all squared. If we factorize above the line, common factor 2, trinomial factorization, check that. And then we change the division to multiplication, swap the order, a plus b above the line now in the numerator position, and at the bottom also recognize this as a perfect square, a minus 2b all squared, and then multiplied with, can you see what happened here? We took out a negative 1 to change the order of the terms in terms of the signs to have a minus 2b rather than 2b minus a, and that is necessitated by the fact that we already have a factor below the line a minus 2b, in this case twice. So if you want to do cancellation, we need to change the 2b minus a into a minus 2b and just retain the minus 1 as part of the numerator in the final analysis. So once we have done that, we have to simplify, see all the like terms above and below, or factors rather, common factors above and below. A plus b will cancel, a minus 2b will cancel in both cases, and then we're left with a minus 1. 2 will cancel with the 2 below, and the result in this case in fact turns out to be exactly the expression minus 1, which can also be viewed as an algebraic fraction for that matter. In the third problem of this tutorial, we're given a sum of two algebraic fractions as indicated on the screen, divided by an algebraic fraction on the right. Now in this case it's slightly more complicated. We have to first consolidate this particular sum into one algebraic fraction, and we apply the techniques that we have seen earlier in this video. In this case, amongst others, we need to find the lowest common multiple of the two denominators of the algebraic expressions in the brackets as indicated. So this is 2x squared in this case, and we obviously need to compensate to consolidate the numerator in this particular instance. So for example, the numerator 1 in this case will become 2x if we multiply by the factors that are missing as part of this consolidated denominator, and also in this case we have 2x squared is the same as the denominator of the first term in the brackets, so we just retain the numerator x minus 21y in this case. If we consolidate this, of course, we have 3x minus 21y, and that can then be factorized to give us 3 times x minus 7y for the numerator of the first algebraic expression, in this case in consolidated form as one algebraic fraction. Now this has to be divided by a second algebraic fraction. We can start by factorizing the numerator of this particular algebraic fraction. Just check that you agree with this particular trinomial factorization. Then change the division into multiplication in this case. In other words, the xy, the denominator, becomes the numerator, and the product of the two factors as indicated becomes the new denominator. Now we're ready to cancel. You can see that we have common factors above and below the line, and we cancel all common factors in this case that can be cancelled, the x for example, and so on, and we have the final format of this particular expression as the algebraic fraction 3y divided by 2x multiplied by x plus 6y. Finally, in the fourth problem of tutorial 3, we have the following situation. The quotient of two algebraic fractions added to another algebraic fraction. Now be careful here. In this case, we first apply our technique to find the quotient of the two algebraic fractions, and after that we consider the difference between the resultant algebraic fractions. So first of all, focus to change the division into a multiplication as we did before, and factorize the numerators as well as the denominators in this case. Now go through this exactly the same as what we had before, very similar. Trinomial factorization, common factors, etc. And in this we recognize as a perfect square again. If we take the numerator and we make it the denominator for the reciprocal to change the division to multiplication, we notice that this is just a minus 2b all squared, and so on. So now we multiply these two algebraic fractions together first. If we do that, we see some cancellation of factors above and below, a minus 2b for example, and the a plus b in this case, and then we have a result here for the product of these two algebraic fractions as being 2 divided by a minus 2b. That is all that remains in this case. Now, you see the a plus b also cancels with the a plus b a second time for this factor. Then we consider the difference of the two algebraic fractions. But in this case, we're very lucky. We have the same denominator in both cases. Did you notice that we have changed the plus for the second term to a negative? That is to facilitate the denominator to become a minus 2b instead of 2b minus a. And that was done exactly to facilitate the denominator of the second term, the second algebraic fraction, to be exactly the same as the first algebraic fraction, which we have generated by taking the quotient of the two algebraic fractions. And that is important, since whenever the denominators are the same, we may just, in this case, subtract the numerators from each other to consolidate these two algebraic fractions into one. And in such a case, we have 2 minus 2 is 0, and 0 divided by anything, of course, is 0. So your result in this case is just 0. In lesson 3 of this video, we consider simplification of compound algebraic fractions. We start by explaining the structure of compound algebraic fractions. A compound fraction is a fraction in which the numerator and or the denominator contain fractions of its own. The so-called inside denominators are those denominators which form part of fractions in the denominator and or numerator parts of the compound fraction. The idea is to eliminate all these inside denominators, in other words, to change the compound fraction into an ordinary algebraic fraction. That is, again, by utilizing the concept of the least common multiple as before. We will now consider an example of where we simplify a compound algebraic fraction. The strategy again, we have to multiply the numerator and the denominator of the compound fraction overall with the lowest common multiple of all the so-called inside denominators. Let us consider the following example. Here we typically have a compound algebraic fraction. That means that in a numerator position we have algebraic fractions appearing separately, and also in the denominator position for that compound algebraic fraction we have algebraic fractions appearing as such. The inside denominators in this case will be the denominators of these algebraic fractions which appear as part of the numerator and also the denominator in this case. In our case here it is just m and k respectively. Now what is the LCM of m and k? Clearly m times k. And the strategy now is to multiply by this LCM divided by itself. In other words, multiply by 1, so as not to change the overall compound algebraic fraction that we started out with. If we do that, we see that we have simplification if we multiply the m times k with the numerator and also the product m times k with the denominator in such a case. Check carefully, if we multiply through, that you get this particular new algebraic fraction, which is not a compound algebraic fraction anymore. It's an ordinary algebraic fraction of the type that we have seen before. If we multiply m times k with this particular numerator, we get k squared minus m squared. Check that. And similarly, if we multiply m times k below the line, we get this particular trinomial k squared plus 2mk plus m squared. And all that is left to do now is to factorize the numerator and the denominator if possible, and then simplify. In this case, we can simplify this fraction since we have a common factor above and below the line, k plus m. And finally, the original compound algebraic expression can be simplified to the algebraic expression k minus m divided by k plus m. In the second example of simplification of compound algebraic fractions, we have a similar situation. Can you see we have algebraic fractions above and below the line for this compound algebraic fraction that is given? In this case, the question is, what is the lowest common multiple of all the inside denominators? Now let's first identify the inside denominators. In this case, it is the denominator x minus 1 in this algebraic fraction above the line. X as well for the second term is part of the numerator in this case. Below the line we have the denominators x and obviously 1 over 1, which means we have a 1 as a denominator as well, inside denominator for that matter. What will be the lowest common multiple of x minus 1, x in this case, and 1? Clearly, it will be the product of the two, x times x minus 1. So we multiply, as we have seen before, with the expression x times x minus 1 divided by x times x minus 1. You see, this is plus 1 really. We do not change the original compound algebraic fraction. So this is the LCM that we were looking for of all the inside denominators, and once we have this type of product, we multiply the numerators together and we see that we have simplification. X minus 1 will cancel with the x minus 1 in the first term, and for the second term the x will cancel with the x, and similarly for the denominator, if you multiply by x times x minus 1, we will have cancellation of the x's, and this then results in another algebraic fraction, which is now not a compound algebraic fraction anymore. And we can simplify this exactly as we did before for such cases. Consolidating the numerator in this case and the denominator, we see that we can simplify if we expand in a denominator position and collect terms, like terms. We have the expression or the algebraic expression 2x minus 1 divided by 1 minus x squared, finally, as a simplification of the original compound algebraic expression. In the third and final example of simplification of compound algebraic fractions, we consider this particular problem. How do we simplify this compound algebraic fraction? Well, the question again, what is the lowest common multiple of all the inside denominators? Let's identify the inside denominators. In this case, it will be x minus 1. And then for the rest, above and below, it will just be plus 1. So the LCM in this case is clearly x minus 1. And we multiply by x minus 1 divided by x minus 1 as before. And then we consolidate and simplify the result. So multiplying above the line in the numerator position, the numerator with x minus 1 gives us the expression as indicated. Let's check that. X minus 1 times x, and then x minus 1 times 1, and then it will cancel for the third term if you multiply, and we're left with plus 1. Similarly, below the line we have 2x into x minus 1 minus x minus 1 and a minus 1. So we have to consolidate here and simplify, and if we do that, we see that the simplified version or format of this particular compound algebraic fraction just becomes x divided by 2x minus 3. Our final tutorial for this particular video requests you to simplify the following expressions completely. And here, of course, we have two compound algebraic fractions, and we have to simplify. Take note, with number 2, we have one compound algebraic fraction divided by another, so it becomes multiplication with the reciprocal. Remember that? We can combine it in that way as well. At this point in time, I suggest that you pause the video, do tutorial 4, and then come back and view the solutions. Let us have a look at the suggested solutions for tutorial 4. In the first case, first problem, we had to simplify this compound algebraic fraction. Now the question is, which will be the inside denominators in this case? Clearly it will be a above the line and a squared below the line. These are the inside denominators of the compound algebraic fraction, and the LCM of a and a squared will be just a squared. So we multiply by a squared over a squared as before. Multiplying through above the line, we get 2a squared plus a. Below the line, if you multiply through by a squared, you get 1 minus 4a squared. So we reduce the compound algebraic fraction to an ordinary algebraic fraction, which we can actually simplify through factorization as we did before. Above the line, we have the common factor a into 2a plus 1. below the line, we recognize this as the difference between two squares, which means the factorization becomes 1 minus 2a multiplied with 1 plus 2a in the denominator position. We have a common factor above and below, and if we cancel that, we get the final format for this particular compound algebraic fraction, namely a divided by 1 minus 2a. In the second problem, we had a compound algebraic fraction divided by another compound algebraic fraction. Now the first thing to do here is to change the division into multiplication with the reciprocal of the compound algebraic fraction on the right. Clearly we just swap the numerator and the denominator positions. After this, we can actually reduce the left-hand side factor, which is a compound algebraic fraction, on its own, and then separately the right-hand side factor like we did before. The inside denominator for the left-hand side factor, this compound algebraic fraction, will just be 2. So we multiply by 2 over 2 and reduce this to an ordinary algebraic fraction, as we can see on the screen. And similarly for the right-hand side factor, which is a compound algebraic fraction in this case, we look at the inside denominators. In this case it's 3 and x, and the LCM of 3 and x is just 3x. We multiply this particular compound algebraic fraction with 3x divided by 3x as before, and we reduce this compound algebraic fraction to an ordinary algebraic fraction in this way. See, if we multiply through, in this case we just have 2x squared, and if we multiply 3x with 1 in this case, we have 1 divided by 3, that is, we have just x, and of course if we take it as a common factor, we have a plus 1. So we can factorize even the result at the same time, and we see we have above and below, in this case a common factor, namely 2x plus 1, which will cancel, and the final simplified version of the original division or quotient of compound algebraic fractions will be, in our case, as can be seen on the screen, x multiplied with 2x plus 1 divided by 3 multiplied with 2x minus 1. Just check and see that you can reduce to this particular format in this case. We have come to the end of the second video on basic algebra. Remember, you have to consult textbooks for additional examples and attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this video. Repeat this procedure until you are confident. In other words, do it as many times over as possible. Do not forget, practice makes perfect. Goodbye.